Okay, so we doing all right on this thing? Do we got, what's the angular acceleration on this thing? 2.44? We got that all right? Any questions on that? I think the angular acceleration was 2.44 on that. Yep. I don't remember, but I think, okay, it's 2.44? Great, okay. So do we got any questions on that, 2.44? For that? So that's alpha. Okay, once you got alpha, you can find the mass, and that's about 9.21 slugs. And then once you got that, you can find, you can then go ahead and find the reactions. So there's two things you do on the reactions on that thing. First one is dynamic reactions. The other one is static reactions. And as I was saying, to get the dynamic reactions, you want to use that sketch up above. All right, so you should have got to alpha equals 2.44 radians per second squared. The mass then is 9.21 slugs. And then, okay, so that's what we got there. All right, and then you want to find those. So then you get two sets of reactions. So you're going to get one set basically like that. And then the other set will be here, which is more of a statics type reaction. That thing's going to pull back because of the moment imparted by the weight. You'll have a reaction going that way, and then you'll have them up at the hinges. Okay, so that's just going back to statics. And then also you're going to have dynamic reactions, which you'll want to calculate. Okay. So we doing all right with that? I just figured it'd be easier to separate the static and dynamic reactions than it would be to try and combine them. It just gets a little messy if you try to do that. So figured there'd be just separate reactions. One for statics, one for dynamics. Okay. We got any questions on that one? So we'll go over this stuff in some detail tomorrow. You know, this is basically, I'm just trying to get you a review, you know, for some stuff you might see on the final. So let's look at this other one here now. Now this is a bicycle handout. It's near the end of the homework handout, so I think if you're on Moodle. And where are we here? Is that the very end, or where did I put this thing? There we go. Yeah, it looks like that, okay. So what we've got here is we got a bicycle rider, obviously, or maybe not with my artistic abilities. That's a bicycle rider, okay. We got a bike and a rider moving to the right. The mass of the bike and rider is 90 kilograms. A moment of 38 Newton meters is exerted on the back wheel of the bicycle. I gave you the radius of gyration of the back wheel and its mass. Front wheel has a mass of 70 kilograms. No, 0.7 kilograms. That'd be quite a front wheel if it was 70. It's 0.7. Okay, treat it like a hollow ring. But, you know, so front wheel's pretty straightforward. It just has a little bit of a hub, and then most of the mass is in the rim. So I just said treat it like a ring. The back wheel has the sprocket and all that, so I gave you the moment, the radius of gyration instead. Let's find the acceleration of the bike and rider. Assume the back wheel doesn't slip. Check your assumption. Be sure to use dynamic reactions when you check slipping. The coefficient of static friction is 0.35. Coefficient of kinetic friction is 0.3. All right. So this is kind of a more of a general plane motion type problem. Okay, so now this one, I wouldn't try and treat that thing as one object. You can do it, but it's a bit tricky. So how about getting a separate free body diagram of each wheel to start that problem, okay? So why don't you see if you can do that. And, and work with anybody you like, or ask me questions, or ask your neighbor questions, or do whatever the heck you like on that, okay? But let's get a free body diagram of each wheel. Y'all remember y'all ridden bikes, see? The back wheel has the sprocket on it. Front wheel doesn't have much at all. Front wheel's just kind of a free wheel, okay? Right? So remember the stuff on drag wheels and drive wheels and all that stuff, okay, when you draw this stuff out. Any questions on the wheel or anything? Remember the stuff with drag wheels and drive wheels and how they act differently. That's kind of an important part of this process here. Understanding that.
was the force of friction in the back wheel against the direction?
Okay, questions coming about the friction on the back wheel. What makes the bike go?
Friction. So
Which way you gotta go?
it's
Friction is the drive force. What you're trying to do is spin that tire faster than it wants to go. And the road says, I'm going to do that, and it pushes back. That's how a drive wheel works. It's different than a drag wheel. Okay? So yeah, we're just going over in class here. The friction on the back wheel acts in the direction of motion because that's the drive wheel. Okay, and that's the main difference between a drive wheel and a drag wheel. A drive wheel has a moment actively applied to it. It tries to spin that wheel too hard, and friction resists that spinning. And that's what makes the thing move. Okay? I'm going to pause the recording here just so y'all aren't online, aren't just watching nothing happen here. All right, y'all got free body diagrams? Okay, because I was noticing maybe half the people don't, which is not really great. But let's have a look. Okay, we're doing free body diagrams of wheels, right? So they're circles, kind of. There we go. All right. So on the back wheel, we got the normal, or whatever you want to call that. Now, you got to be a little careful on that one, but we can get to that later if we got time. We'll just call this, let's call this F, and we'll call this B, front and back. So this is FB, and then we got the normal, right? Now, there's just two more things on this, and what are they? The friction. Okay, yeah, we start with that couple. The couple's doing that. And the friction is resisting that because this is a drive wheel. Okay, like so. All right. And then on the front wheel, what do we got? We got FF. We got the normal. And then we've got one more thing, and what's that? Friction which way? Yeah, it goes to the left, because that's a drag wheel. We're just trying to push that thing across the ground, and it just doesn't want to do that. So we got frictions. Now these frictions are not equal, okay, because the thing's accelerating. So they're not equal to one another. But, I was noticing a number of you didn't have free body diagrams, and this, there isn't much to them, but if you just have that picture, if you just do your thinking and get that picture drawn, or those pictures, you can quit thinking now and just do equations, okay? Just pull the stuff off and do the equations. That's all you got to do, okay? All right. So if you do, now, and let's just, so why don't you write up equations for these wheels, okay? And just focus on them, okay? And for each wheel go, I don't know if we'll need all of them, but go some of M and some of F for the wheels, okay? Given what you see there. I guess, being as we're doing dynamics here, what else should we put on these things for dynamics? Acceleration, yeah. A. Now, do the accelerations equal? Yeah, I hope so, okay. And how about the alphas? Are they the same diameter of the wheels? I can't remember. I think they are. They should be, okay. Alpha. All right, there you go, okay? So those are the pictures. And then when you see those, just draw up the equations. And again, you don't got to think about it once you got those pictures drawn. And see, the pictures aren't that bad, really, right? They're pretty straight up. So just write up those equations. That's the next step. Doing all right on this?
How do you find how the weight is distributed?
You're gonna have to, okay, you're solving for friction. You don't need the normal to find the friction. So I think you're gonna need that acceleration to find the normals, because they're dynamic reactions. So I think you're going to have to work with the unknowns you've got and find what the frictions are. Then once you've got them, find the acceleration. And once you get the acceleration, find the reactions, the dynamic reactions. That's probably how to do it.
So for some of fx, for some of fx equals ma.
Yeah.
Does this m include the weight of the?
We're analyzing the wheel. We're pulling that off. So you can make a three-body diagram out of whatever you want. And actually, oh, you're right. Yeah, I screwed up on that, didn't I? All right, I'm sorry. Yeah, we got a few things going on these. Thanks. All right, let's get this going. Oh, we're going. Okay, good. All right, so what else do we got going? I'm sorry about that. There we go. That bike's going to be pushing that wheel, isn't it? I forgot about that one. And what's the bike going to do to this wheel? Push it right or left? Yeah, I think left.
Would that be equal to the force of friction?
No, because that would be static equilibrium, and it's not. It's dynamic. All right. Okay, so that's going to start limiting which equations you can really effectively use, isn't it? Okay, because that really starts to get to be a little messy now. What's your way out of this conundrum? Which equations would you use?
Still use the moment.
Yeah, I think, see, when you do that moment, you're going to go about the center of the wheel, right? I don't think I want to do moment down at the bottom, because that's going to, I want to get rid of those force of the bike forces. So I think I'll take moments about the middle. See what you can do with that. Everybody good with this? Anybody got like conceptual questions on what's going on here? What we're doing, we're pulling the wheels off of the bike essentially and analyzing the wheels. That's what we're doing on this, okay? So if we do that, we've got to show how the bike affects the wheels, what it's doing to the wheels. Okay? So I'm showing those forces. I put the forces down, but I also need to put the forces to the right and left. But they complicate things. Okay? They introduce unknowns. So I think I'm going to want to get out of that by taking moments where those forces are applied. That'll get rid of a lot of those unknowns. Okay. So if I take moments about the middle of the back wheel, what are the unknowns going to be then?
Force of friction and acceleration.
Yeah, alpha really, yeah. Okay. And then the front wheel, what do I got?
Force of friction and acceleration.
And yeah, alpha, acceleration, whatever. All right, but what can I say about alpha for the front and back wheel? They're the same. So now I've got it down a little bit. So let's start with those moment equations and see what we can do with them. Okay. Yeah, okay. You're going to need moments of inertia here, right?
Would you set these up to solve for the acceleration or just alpha?
For these?
Yeah.
Now you can relate alpha and A together through the radius, so they're really one unknown. Now the acceleration is going right through the center of the wheel too, so A will not directly enter into this. Okay. Now we're going to have to do one other little trick on this, but we'll get to that. Let's just do those moment equations next, okay? Now remember, those forces of friction are not equal to each other. They're different. You got questions here, let me know.
With the radius of gyration, we're just multiplying it by the mass, is that it?
You square the radius of gyration and multiply by the mass. Yeah, to get the moment of inertia of that back wheel, just take the radius of gyration, square it. That'll get you length squared times the mass, and that'll get you the proper units. Okay? Front wheel, just treat it like a ring. Mr squared is the equation.
So I can find those two, but I only have two equations.
Right. Oh, right. Yeah. Okay. But you do have two independent equations, right?
Yes, I got this and
So now you need one more equation to come up with the frictions. So you're going to want to, and give this one a little thought. Think outside of the boxes.
why?
Not why.
That's
Well, yeah, I guess we'll do the very complicated process of elimination there. See what you can do with that.
for the person, did you do it for the okay.
Not wide, back. I have to remember that one.
Okay, for starters, get those moment equations about the centers of the wheel, okay? For those, you'll need the moments of inertia. So mk squared for the back wheel, mr squared for the front wheel. Let's see effective R. Effective rate.
So he's actually isolating all these rules in the way, so you're just looking at spins and no, it's just the since it's about this one, you're gonna look at distance. Well, are you talking about dosage of time? You're just isolating this really here, and then that ends under the cover. Yeah. Well, no, but if you're doing
What? Where'd they come from?
yeah, like
K squared and then R squared.
yeah, so
Oh, you get a different number?
yeah. Back wheel, well, so it's 0.9 times 0.29 squared. Like that.
0.29 squared.
Yeah, that's also good.
And I had some different versions of this thing floating around. Oh man, yeah, I'm looking at the wrong one. There we go. That's 28. Yeah, I got a bunch of different versions of this, so that's fine. So,
It's just seven, alpha instead of there's no point.
yeah, I've got, those are bum numbers there. I'm sorry. I've got different versions of this thing floating around. So what was that back one? 0.0 what?
0.07565.
Okay, how about the front one?
I got 0.07168.
Yep.
168, 17. Okay, I got room for 3. So there we go. So yeah, I've redone this problem a few times. I was looking at an old key. All right. So those are the moments of inertia. All right. So 0.0757 and 0.0717.
Two equations and three powers.
Yes, and so you need a third equation that makes this all work. No, it's the entires. Let's see.
Yeah, no.
Y'all want to have a look at those real quick? All right. So for the moment equation here, we'll call clockwise positive because everything's going clockwise, okay? So what do we got? We got 38 Newton meters.
Those were the
And then minus, what's the radius of that back wheel? Is it 0.9 or? 0.9 would be pretty big. 0.32? Oh, that's a good radius, okay. So that's 0.32 times the force of friction. And that's going to equal I sub g times the unknown alpha, right? And we got I sub g. Is this the 0.717? Okay, alpha.
76
Oh,
for the back wheel.
That's correct.
is that, okay, well, we'll just go with that. We got, okay? So we good with that? Now we got another one. And what the other one's going to be here is this is going to be a little simpler here. This is just 0.32 force of friction. Now that's for the front. This one's for the rear here. So the back, rear, whatever. All right. And that's just equal to this I in the front. And what was that again? 0.072. And this is going to be times alpha, all right? Is that basically what we got going on here for these moment equations? Okay. That's 5, is that 5,7 or 1,7 there?
For which?
This one.
That should be 5-7.
5? Okay. .07, okay, yeah, so we just, sorry, let's get this cleaned up, sorry. Okay, so now the problem is you got three unknowns, right? You got alpha, and so let me do one thing at a time here. So 0.0757 times alpha. Now the alphas equal each other because the wheels are the same diameter, same size, and they're both, the bike's moving at a certain rate. So the alphas equal each other. We're assuming no slipping, so we got A is our alpha, right? Now the problem is we've got three unknowns in these equations. Alpha, force of friction on the rear, and the force of friction on the front. So the problem here is going to be we need to generate one more equation that's going to include at least, preferably all of those variables, okay? Now the one thing that I'll point out here is we know the radii. So let's go ahead and wherever we can find the room, let's put down this other little equation, and that is that A is equal to 0.32 times alpha. So alpha then is the inverse, A over 0.32. So let's see, we're about out of time. So I think, why don't you just give this some thought over the evening? We'll go over this tomorrow pretty well. But think about it. What's the other equation you can use that'll involve the variables we're working with without involving another one, okay? Because if we don't want to just generate a third equation and introduce a fourth variable, that's not going to help us at all. So we want one more equation that involves those three variables, okay? And yeah, the thing on this is don't just focus on a wheel any longer, and anything's open. Anything you want on this problem is wide open. So think about how else you could come up with another equation. And there is one that I found, okay? And we'll cover this thing tomorrow. We'll go over the door a little bit tomorrow too. So have a look at those tonight, okay?